New section, summation on infinite sets. Now before we start this section, let us recall that in the previous section we went through the notion of countability. We saw what countable sets are, and ultimately we ended up proving that the set of rational numbers is countable. And in the last exercise, which we solved in the last analysis video, we in fact produced a concrete bijection between the set of rational numbers and the set of natural numbers. Now here we are going to see this new concept of summation on infinite sets. So, and the infinite sets that you see in this title, they are going to be countable in the beginning, and we are going to extend that definition to uncountable sets also. But let us first see this summation, what it is going to be in the first definition, and in this definition the set is going to be countable. So here is the definition. Definition 821, and it has a name also, series on infinite sets. Series, sum, these terms are used interchangeably. So the definition goes like this: let X be a countable set and let f from x into the set of real numbers R be a function. So we have a countable set x and a real valued function f with x as its domain. We say that the summation of f of x as x varies over x is absolutely convergent if for some bijection say G from the set of natural numbers onto X, the series summation f of G of n, where n varies from 0 to infinity, is absolutely convergent. Okay, so the definition is not over yet, but let's try to understand what we have written so far. So we are given a countable set x, that means it is infinite. X is infinite and its countable means it has a bijection with the set of natural numbers. One such bijection you see here, G. And a real valued function f is given whose domain is x. And now we are saying that a sum, which is a symbol that looks like this, we are calling this symbol a sum, will be called absolutely convergent if for some bijection like this, which you know exists because x is countable. For one such bijection, this infinite series is absolutely convergent. When that happens, then we say that this sum is absolutely convergent. Note a number of things here. We understand what this series is, because you see, for every natural number n, g of n is going to be what? G of n is going to be an element in x, and on that if you apply f, then you are going to get a real number, because f is a real valued function defined with domain x. So this infinite series is a usual series of real numbers, and we know when it is called absolutely convergent, namely when this series is convergent. And we are saying that in this case, this sum is absolutely convergent. Notice carefully that this sum itself is not an infinite series. I mean, in the what we know as an infinite series, this is actually not an infinite series. Yes, it also involves real number terms, because for every x in x, f of x due to the nature of f is a real number, and since x is infinite, so there are infinitely many real numbers involved in this symbol. Okay. However, the symbol itself is not an infinite series. Why? Because how does an infinite series look? An infinite series, for example, looks like this, where an is some sequence of real numbers. Is f of x a sequence of real numbers? No, these are just functional values. Okay, it's not a sequence of real numbers. I mean, the way it looks, it's simply, you can see it's not a sequence of real numbers. There is no pattern in which these real numbers are appearing that can be understood from this symbol. In fact, this symbol tells us nothing about any pattern whatsoever in which these f of x values appear in this symbol. Here, however, in any infinite series, such a clear pattern is there. A0, A1, A2, these are the sequence, I mean, this is the sequence of terms appearing in the series, and from these things, these terms, or from the sequence of terms, we can construct the sequence of partial sums for this series. And when this sequence of partial sums converges to some real number, we say that this series is convergent and has that real number as its sum. Okay, that is our usual convergence of a series of real numbers. This, however, is just some abstract symbol. Still, we are calling it a sum. Now, just from the way it looks, this symbol, the way this symbol looks, and it looks like this series symbol. So it looks like we are actually considering the sum of all the functional values that this function is going to give us as x varies over x. That means countably many functional values. However, because of a lack of pattern in which those values are to be considered in this sum, it's not exactly an infinite series. It's, however, still an infinite sum. No order is there. Still, this sum is going to be called absolutely convergent if for some bijection g, this series is absolutely convergent. Now you can of course understand that by choosing one such bijection, actually the pattern that is or the order that is lacking in this sum, we have provided that order, because now we know in what order we are considering these x values. So our first value from capital X is g of 0. The second value is g of 1. This bijection G orders the elements of X in a definite manner. It arranges the elements of X in a sequence, and that sequence is G of n. So now after we have provided this sum with a sequence and order, it becomes an infinite series, and when this infinite series is absolutely convergent, we are saying that this symbol or this sum, whatever you may interpret it as, that is also absolutely convergent. Okay, now comes the next part of the definition, and when this happens, when this is absolutely convergent, we define the sum or more precisely we define the value of the sum as this. Its value is defined to be equal to the sum of this infinite series. Okay, fine. The first part of the definition, there is no problem with that. If such a G exists for which this becomes absolutely convergent, then this is called absolutely convergent, or this is defined to be absolutely convergent. Okay, now just looking at this part of the definition, a question may arise. You may also come across some other bijections. X being countable does not mean that there is only one such bijection. There may be many such bijections. Okay, in fact, there may be infinitely many such bijections. Now, you may come across one bijection for which this is not absolutely convergent. Without thinking too much of what the actual thing is going to be, just on the face of it, we can just simply say, okay, maybe there is one G for which this is absolutely convergent, maybe there is another bijection H for which this is not absolutely convergent, say. However, note what the definition is saying. We say that the sum is absolutely convergent if for some bijection, if you find at least one bijection G for which this is absolutely convergent, then itself we are defining it to be absolutely convergent. So there is actually no problem. We just need at least one such G for which this one is absolutely convergent, then we are going to say that this is absolutely convergent. But there is a problem with this second part of the definition. When you have absolute convergence, then you are defining the sum, the value of this symbol to be equal to the sum of this series. However, you have got one G for which these things have happened, you may get another bijection also. Just now I have said that there may be multiple such bijections. So if you are having, say, another bijection G prime from n to x, for which also the corresponding series, that is this one, is absolutely convergent, then according to this definition you should also define, or you should also have the value of this sum equal to this. Now there would be a problem if these two real numbers are not the same, because if that is the case, then this definition is not well defined. It will not give you a single value of the sum, but possibly many different values, and that will then be useless. Fortunately, that is not the case. Even if you use another bijection, you are going to get the same sum, and this is why we need absolute convergence. Let's address that now. Okay, so let's say this is the situation. You have G, you also have G prime. For both of these bijections, these two series are absolutely convergent. Okay, now we need to show that this sum is equal to this sum, and this is where our previous result that we have already seen from the theory of absolute convergence of series, that will now be used, which is proposition 743. So roughly, briefly, what this proposition, let's just recall the statement. What it said is this: say we have an infinite series of real numbers that is absolutely convergent. This is absolutely convergent. Then if you have any bijection f from the set of natural numbers to the set of natural numbers itself, then this series a f of m, if you want you can write n here also, but maybe that will look confusing, so we are using another variable name. So in this series, what we have done, we have just modified the suffix values by replacing in place of n we have written f of n, that's it. Then this is also absolutely convergent. Let me write in short like this: absolutely convergent. And because it is absolutely convergent, it will also be convergent. Convergence is the consequence of absolute convergence. And then what is its sum? It turns out that the sum of this modified series is equal to the sum of the original series. And this is the result that tells us that we can rearrange the terms of an absolutely convergent series. Its absolute convergence will not be affected, and its sum also will not be affected. It will still continue to be absolutely convergent, and its sum would be just the previous sum, that's it. So we can now use that here to show that these two series are actually the same thing, or they are going to have the same sum. Not the same thing I should say, but they are going to have the same sum. But how? Okay, so let us again write the two functions. Our original g was a bijection like this, and g prime is also again such a bijection. Now that means what? It means that we can consider, for example, this composition of g prime inverse and g. Okay, so when we apply this composition to some element in the domain of this composition, what will be the domain of this composition? N. So you take a natural number, apply g to it, you are going to get an element of x. So now you are here. On that, if you apply g prime inverse, then that will take you back to n. So that means this composition maps n into n. Is it a bijection? Yes, it is a bijection. Why? Because since g prime is a bijection, first of all, due to the fact that g prime is a bijection, its inverse exists, and then the inverse itself is also a bijection, and we know that the composition of two bijections is a bijection. So the composition of this bijection g prime inverse and g is a bijection. So now you see that you have a function like this that you need in this proposition. So now we can apply this function and say that if we change the suffix of say this series in place of n, see there also we had n, of course we wrote n in the suffix, but you can understand that you can write it as a of n also, because after all an is a sequence, and any sequence is a function with the set of natural numbers as its domain. You can change the domain a little bit, but here we have the set of natural numbers. So here in place of a of n you have f composition g prime of n. So that means if you change this series, this one, then you are going to get this m equal to 0 to infinity f of g prime of, in place of n there what we wrote f of n. Now here in place of this function we have g prime inverse composition g. Of m. This series here takes this form, this one, and this should also be absolutely convergent, and it should have the same sum as the original one, that means this one. But here there is a simplification. You can see that g prime inverse and g prime cancel out, or more strictly speaking, they give us the identity map, which just vanishes inside, and we are left with what? F of g of m, where m varies from 0 to infinity, which is just this. Yes, you have n here and here you have m, but that is not going to make any difference, because these are just variable names, they are dummy variables. So that's how, in spite of having this g in the definition giving you the actual sum of this infinite sum, the actual value of this infinite sum, the sum ultimately does not depend on g. In fact, if you take now you can see that if you take any bijection in place of g, that is also going to give you the same value. So that is why the definition is well defined. Whenever your sum is absolutely convergent, in the sense that one such series is absolutely convergent having chosen any bijection, then the sum given like this, given by this equation, is uniquely determined. Okay, so the definition is well defined. Now using this notion of sum over countable sets, we can state and prove a very important result called Fubini's theorem for infinite series. So that's the next thing. There is a Fubini's theorem for integrals also, which we will see towards the end of this book. So that is the next thing, theorem 822. Fubini's theorem for infinite sums, infinite series, same thing, for infinite sums. Okay, so let us now see the statement. Let f from the Cartesian product of two copies of the set of natural numbers into R be a function such that the sum, this sum, f of n comma n has the ordered pair n comma m varies over this Cartesian product is absolutely convergent. Then we have some equalities, and the equalities look like this. Summation n varying from 0 to infinity, summation m varying from 0 to infinity, f of n comma m is equal to this sum which is equal to summation f of n comma n, m comma n belongs to, so here we switch the order of m and n, and that itself is equal to again we are going to write a sum of sum like this one, but we switch the order. M varies from 0 to infinity of summation where n varies from 0 to infinity, and this is fn comma m. Okay, so let's now see what this means first of all. So in the beginning itself we are given again a real valued function. From just like previously we had a real valued function from x into r, where x was a countable set. Here in place of x we have this Cartesian product. Recall that in the previous section we have in fact shown that this is a countable set, and it came on the way, when we were going to prove that the set of rational numbers is countable, on the way we had to prove that this is countable. So it is the kind of function that we need in order to define a sum over an infinite set or over a countable set. Fine, so we have our function, so we can now consider this sum. Note that instead of f of x, here we have f of n comma m, because that's how a general element in this x looks like. So our sum looks like this, and say it is given that this is absolutely convergent. Now we know what this means. Now we know what it means for this sum to be absolutely convergent. Let's see what that actually means in this case. So what it is going to mean is this. Say you choose some bijection which you know at least one will exist between n and our new x, such that f of g of, let me write I in order to avoid any confusion. This series is absolutely convergent. There is at least one such bijection for which this series is absolutely convergent. You can understand that these g of i's are nothing but the elements of n cross n arranged in some sequence. So these are ordered pairs. Actually they are ordered pairs. So one such series is absolutely convergent. That's what it means for this sum to be absolutely convergent. Then this double summation equals the original sum, which according to the definition in fact equals the sum of one such series. And then here we can switch the order of these coordinates, or if you are just simply considering this m comma n to be any element in this n Cartesian product n, then here you have switched the order. So f of what you see here also there is a function, because our original input is m comma n. It's that function which switches the order. Okay, so that thing is there. So it is another such sum, and that again is equal to again one such double sum, but here we have switched the summations, and they all have the same sum. We have to prove this, which we will do in the next video. Today we are not going to do that, but note that only the absolute convergence of this is given. The absolute convergence of this third sum, which is slightly different from this one in that the order of these coordinates gets switched, that also has to be established. It also needs to be shown that this is absolutely convergent and has the same sum as this. That is one thing. And also we have to make sense of the convergence of this double sum first of all. and correspondingly there is another one, this double sum. They will be similar, and then you have to somehow prove that these also have the same value. The advantage of Fubini's theorem is that you can switch the order of these two sums, which sometimes becomes extremely important, and in fact you need to do such things in calculations. For example, you have one sum and inside you have some other sum, but it's difficult to perform this inner sum because the way things go in this kind of symbols is that what is inside you do that first, and then you gradually come outside. But say this sum is pretty difficult to perform. If somehow you are able to switch the order, and now say this outer sum, which here has become the inner sum, it is easier to perform. Then you can get your job done quite quickly and easily. So that's why Fubini's theorem is quite important. Its proof is not going to be elementary, it's going to be a little lengthy and somewhat difficult, but we will go through it step by step systematically, so don't worry about that. So this we will do in the next analysis video, and the next upload is of course this coming Tuesday, and what we are going to do on Tuesday, you see it will be there in the description. So that's just it for tonight. If you want to say something about these things, or if you want something, you can mail me. My address will be there in the description, and you can also comment, you can write comment in the comment section below. So that's just it. I wrap things up for tonight. So see you on Tuesday. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.